Is this okay?
Mm-hmm. I think that's okay. Okay, so we will start this special seminar. It's a pleasure to have Mehrdad talking about his work on the spin of primordial black holes.
Thank you. Yeah, maybe. Oh no, there is a big piece here. Two big pieces. Thank you. All right, so I'm going to talk about the spin of primordial black holes. This is based on work that I did in collaboration with Andrei Gruzinov and Jorge Norenia.
It's a friend.
Yes. So I start by just telling you, give some little introduction about primordial black holes. Primordial black holes are black holes that are supposed to be formed at earlier stages compared to the time when we have usual structure formation. That's why they call it primordial. And one of the main reasons that they are interesting or they are considered is that they are a candidate for dark matter. It's actually a very minimal candidate for dark matter because it doesn't require introduction of a new particle, for instance, anything beyond a standard model. And there was renewed interest in primordial black holes after the observation of black hole mergers by LIGO. So recently they have become a bit more popular, are being discussed more. I should say that there are also a lot of constraints on them from many different directions, both cosmological constraints and astrophysical constraints. So there are big chunks of the parameter space that are ruled out, and depending on who you ask, you might hear the answer that they cannot be a candidate for dark matter anymore. At least there seem to be some indications that for most range of masses, they cannot be formed 100% of dark matter. However, the question has not been fully settled yet, and there are more searches that are going to, more investigation that is going to happen in the future. So it is useful to have a good understanding of the properties of these primordial black holes. In particular, we want to understand the mass distribution, number density, and spin, so that we can put better constraints or we can distinguish them better from the observations. So that's why the subject. Now, there are also, of course, one should discuss the scenario to produce these primordial black holes. And there are various scenarios to produce them. One very common one that I'm going to discuss here is to consider them as being formed from the collapse of very rare peaks in the primordial fluctuations, primordial density fluctuations that we have been discussing all this week. So now I'm going to give a little derivation or introduction of how this mechanism works. So let us go back to this metric that we've been writing, and I'm simplifying this metric. So we have one way of parameterizing the fluctuations of the FRW metric, which is using this variable zeta, which was essentially a space-dependent scale factor, and I'm simplifying everything. First of all, I'm not including gravitational waves, and then there is I'm ignoring some small correction to this metric. So why do we like this variable zeta to describe the scalar fluctuation? The reason that we like it is that, well, at least one reason that we like it is that in the minimal models of inflation, it is nearly Gaussian, if I describe it in this particular way. And what it does is that it describes the shape of the constant time surfaces. So if I consider constant time surfaces, then this variable zeta at linear order, it determines the intrinsic curvature of these constant time slices. So if I look at the Ricci curvature of Ricci scalar of these surfaces, that is something like Laplacian of zeta. Okay, now one thing that we can do is that we can consider one of these zeta fluctuations, which is super horizon, very long wavelengths, and try to consider a separate universe model that we have been discussing again. So what's happening in this separate universe model? I can write the Friedmann equation for that separate universe, except that that Friedmann equation has a curvature term in it, which is related to the Laplacian of zeta. So let's write that. We have h squared equals 8 pi g third rho minus kappa over a squared, where this kappa is related to the Laplacian of zeta. Now, for the right sign of this Laplacian, this separate universe will be a closed universe. And as we learned from Rogerio's lectures, that closed universe will eventually collapse. So how does it work? It expands initially, reaches some maximum size, and collapses. So let's determine that maximum size, for instance. At that maximum size, h is equal to 0. And so this kappa is Laplacian of zeta over a squared. Let me associate a size, a physical size, to this region when this turnaround is happening. So then I get some zeta over r squared. That is being of order 8 pi g third rho. In fact, I'm going to drop even this numerical factor, 8 pi third. So what I get is that zeta is of order g rho r squared. Or let me, maybe I should have mentioned this earlier. The reason why I'm doing that is because I mentioned that these primordial black holes are supposed to be formed from the collapse of the high peaks in the primordial fluctuations. Here I'm going to determine how high those peaks have to be so that these black holes form. So at this point, it seems that it doesn't matter how high they have to be. Any peak will collapse. But that's not true, because this separate universe picture that I used is not valid at arbitrarily small scale. So there is another scale in the problem that is called the genes scale. Okay, another thing that I didn't say, I forgot actually. These primordial black holes are supposed to be very tiny. In fact, the observational constraints force them to be very tiny. So they have to be formed well before the matter radiation equality. So we are actually talking about the radiation-dominated era here. And now in radiation-dominated era, there is a condition for this overdensity to collapse. What is the condition? That comes from the genes instability. Of course, if I have some overdensity inside some radiation fluid, if this overdensity is small, then it just disperses in the radiation fluid. There are sound waves in this fluid. It will not collapse. When will it collapse? If it has to be large enough to collapse, to continue the collapse. So there is a condition, and that size, a large enough size, is determined by the genes radius. So R has to be larger than R genes, which is of order CS divided by square root of G rho. So therefore, if I combine these two equations together, what I get is that this initial perturbation that I had, if I wanted to collapse to a black hole, or I want this turn around and collapse continue happening, I need zeta to be larger than CS squared. Now in radiation domination, this CS squared is 1/3. So I get zeta has to be larger than 1/3. Now as you see here, I did only order of magnitude estimates, so you shouldn't take this 1/3 very seriously. The whole point is that this perturbation that we are talking about has to be some order 1 perturbation in order for it to collapse into a black hole. So what is the picture? The picture is that we have this Gaussian random field, zeta, as a function of R. And the way it looks is that it has some random fluctuations. And then at some point, there is one that crosses a threshold, which is of order 1. And that peak that crosses this order 1 threshold, then that one can collapse into a black hole, and that would be a primordial black hole. Now, let us ask what is the probability of finding such a black hole in our universe. So what is the probability of zeta being larger than zeta threshold? We said that this zeta field is to a good approximation a Gaussian random field. So it is a Gaussian random field. The probability of zeta being larger than zeta threshold, which is order 1, so let's just put 1 here for simplicity. That goes as e to the minus 1 over zeta RMS squared. Now, so for instance, remember the Press-Schechter model that Rogerio wrote that was asking basically the same question for a different variable delta. The probability of finding a point above the threshold is proportional to this exponential. There will be some prefactor. But now, if we take this data RMS to be, so again, let us remember this data is the object that is related to the temperature fluctuations of CMB at the scales that we probe CMB. So if we take the zeta RMS to be, to have that value is what is of order 10 to the minus 5. Then we realize that this probability is something of order e to the minus 10 to the 5. So it's essentially 0.
Shouldn't you be calculating this RMS at the scale, at the gene scale R? Because at which scale are you talking
Yes,
about?
yes. I'm assuming that I am putting some top hat. I'm smoothing the field over some particular scale that I want to form the black holes. Yes.
That scale is the gene scale.
Right, but this is we have well. Actually, you want to look at some particular co-moving scale because, so for instance, I want to choose a particular mass for the Jeans scale is always the same thing, right? No, sorry, it's not the same thing. It changes with time. But if I want to yeah, how does it work? I want.
If the power spectrum of Z is scaling, is zeta scaling invariant,
Yeah.
it doesn't matter too much, I guess, right? But
Yes.
if you're
So.
talking about a real space fluctuation, then it's I don't know.
So any particular co-moving scale for the formation of this black holes translates in, because from here what we really see is that this fluctuation essentially when it enters the horizon, it forms a black hole. So the mass of the black hole is fixed by the horizon crossing time of the scale, the co-moving scale that we are interested in. So any mass translates into a a particular co-moving scale.
Right. And the G's length is in fact the horizon scale there, right?
Right. Yeah. So if I'm interested for asking how many black holes of this particular mass I'm going to produce, what I take is I take the primordial fluctuations, I smooth over the scale, the co-moving scale that corresponds to that mass, and then ask how many barrier crossing I have with that smooth. And then the answer will be, so now since this is a scale, if we assume it is essentially a scale invariant, it doesn't matter really what scale I choose. I always get 10 to the minus 5, which will be essentially 0. So in order to get some reasonable number density of primordial black holes which have any observational consequence, the idea is that this data RMS at the scales that correspond to formation of our black holes, this RMS value has to be much larger than the one that we observe at CMB, but of course it should be less than 1 because we don't want too many of them. So therefore, the picture is that, so if you remember, we had a nearly scale invariant power spectrum from the simplest models of inflation. They would predict k cubed times p of k as something that is almost constant. However, this has to change if I want to produce primordial black holes in this scenario. There has to be some sort of a bump here. Maybe it never goes down. And the idea is that there is this range is the range that we probe in CMB. So we have so now this is P zeta, so this is something like 10 to the minus 10 or 10 to the minus 9. And here the amplitude increases considerably at very short scale. So this is somewhere well beyond the matter radiation equality, something that depends on the sky K star, the co-moving wavelengths that corresponds to the formation of this black hole. At that value, the power has to increase a lot. And then you can actually cook up scenarios, inflationary potential that do produce enhancements of the power spectrum around some scales. Any questions so far? No.
So what type of inflationary models that can generate this scale?
Oh yes, I don't know. Well, so what does this mean? You essentially have some kind of a switch inside during inflation that turns on, and then changes the amplitude. Now the simplest, or some kind of feature. So I guess maybe the simplest example to think about is that the potential has, how does it work? So the potential nowadays is more concave one are more fashionable. So it goes like this, and then it becomes flat. And then maybe it continues going like this. So here, what happens is that when I arrive here, I will get to this period which is called fast roll period. So I am on a slow roll. And then here, what happens is that, well, V prime here goes down, and therefore epsilon goes down. Epsilon goes down, P zeta goes up. Usually they are ugly models, I should say. But maybe there are less ugly models that we haven't found, or I haven't seen. Anyway, given a scenario, formation scenario like that, so maybe I should say this should be something, in order to get any reasonable number density, this zeta RMS should be something over the 0.1, not much smaller than that. So given a formation scenario like this, or a power spectrum like this, in principle we have all information to determine the statistical properties of these primordial black holes that form in this scenario. So in principle, we should be able to determine the number density, the mass distribution, and the spin of the black holes in any given in primordial power spectrum. These are the questions that would be interesting to answer, because they have observational consequences. And there had been more work on the determining number density, or relating these first two quantities to the properties of the initial perturbations. The goal of our work was to say something about the spin. So the spin used to be thought to be, or the conventional wisdom was that the spin is 0 for primordial black hole. And really the goal of this work is to quantify this statement. In what sense the spin of primordial black hole is 0 or small. So let us understand what is the reason behind this expectation that J has to be 0 or small. And the reason for that, so why is J small? And by small, I mean there is a natural unit for this J. if I consider a black hole with mass m and gravitational radius rg, then there is a parameter. So this m times rg in the units that c is equal to 1. This has the units of angular momentum. This is actually the maximum angular momentum of a black hole. So there is a parameter that relates the actual angular momentum to this maximum value, which is called A. So this is called the spin parameter, A. And so the question is that why do we expect A to be small? Now, for instance, keep as a pivot point, think about astrophysical black holes. For them, one naturally expects that this spin parameter should be order 1. And the expectation is that for primordial black holes, it has to be much less than 1. So where does this intuition come from? It comes from that same BBKS paper that was mentioned before. So if I consider a Gaussian random field and I look at the very rare peaks in this Gaussian random field, it was shown in this paper that those rare peaks are nearly spherical. And so how do we make it again more quantitative, or how did they make it more quantitative? So let me just draw a picture. So we are considering a high peak in this field. So let's say these are the contour lines of the peak. And the statement is that these contour lines are nearly spherical. So the way to see it, or the way you can quantify it, is to consider the field near the peak and take the Hessian matrix of this Gaussian random field near that peak and look at the eigenvalues of this Hessian matrix. So I denote these eigenvalues, I order them, and denote them by d1 squared zeta and d2 squared zeta. I take the difference of the first two eigenvalues and compare it to the Laplacian of zeta. So the statement is that this difference goes as, and we are looking at a peak with height. So this is a peak with height zeta naught. And the statement is that this difference goes as zeta RMS divided by zeta naught. So therefore, in the limit that zeta RMS over zeta naught goes to 0, the peak becomes perfectly spherically symmetric. So that's the intuition. The primordial black holes are formed from the very rare peaks of the primordial fluctuations. Those very rare peaks are nearly spherically symmetric. And a spherically symmetric distribution, of course, collapses into a Schwarzschild black hole. So what it implies is that this J quantity has to be, one has to be able to come up with a perturbative scheme to talk about this quantity J. What is the perturbative scheme? The perturbative scheme is that when I talk about a black hole, I should be able to consider a perfectly spherically symmetric peak that collapses into a Schwarzschild black hole, on top of which there are little fluctuations which have amplitude of order zeta RMS. So this is what this equation is telling us. I can think of the spherically symmetric peak plus the normal typical fluctuations on top of that. So I have a spherical peak that goes to a Schwarzschild black hole plus order zeta RMS fluctuations. And then in this perturbative scheme, for any parameter of this black hole, I should be able to write a perturbative expansion. So for the mass, there will be m will be some m0 plus some m1, so on. M0 is zeroth order in this zeta RMS, in the sense that if I send zeta RMS to 0, it remains there, while m1 is linear, and so on. And similarly for J, except that J0 is 0. So in principle, it starts from first order and goes to higher order. And similarly for other parameters of the black hole, like momentum and its center. So J0 is 0 because as I send the zeta RMS to 0, the spin has to go to 0. So we have to start at first order in perturbations. And the main claim of this work is that J1 is also 0. So we start from J2. So
You compute J1 and J2 from mass distributions?
I do not compute them, but I will write an expression and show that why it is 0, why J1 is 0.
Okay.
And I do not compute J2.
The physical origin of the spin is this, is that you have asymmetric mass distributions, and when it collapses,
Yeah,
it generates spin.
right.
Is that the intuition?
Yes, that's the intuition, exactly. It's and this is related to what I'm going to say now, which is that so in GR, of course, mass and spin or momentum, these are not quantities that we can define locally. In other words, we don't have any local density of energy or mass or angular momentum. These are quantities that in general relativity, they are defined asymptotically. So that is an important subtlety to keep in mind. We saw here that these black holes form essentially when they enter the horizon. However, at those scales, we cannot unambiguously discuss mass, momentum, and spin of black holes because we don't have right asymptotics. We can talk about those quantities, for instance, in asymptotically Minkowski spacetimes. Now, of course, today, if we see a black hole, it makes perfect sense to talk about its mass and spin. So what happens is that this black hole forms, and then the horizon expands. It becomes larger and larger. The size of the black hole remains the same. So today we can find a region, a locally inertial frame in the vicinity of that black hole, and then those local inertial observers can talk about the spin of the black hole, or the mass of the black hole, for instance, in the same way that we talk about the mass of the sun, or about the mass or spin of the central black hole in our galaxy. These are very well-defined quantity up to very tiny ambiguities that we don't even have precision to measure. So what does it mean? It means that I cannot talk about the spin of this black hole once it's formed. What I can do is that I can wait, and then after long enough time, it makes sense to talk about the spin. So yeah, the intuition is correct. There is some spherical peak with a small asphericity, and that's the reason why this black hole is eventually going to be spinny. But I cannot talk about the spin as it is forming, only after a long time. Or in other words, I can define the spin, but you can define it in your way and we will get different answers. There's no way to unambiguously define it. But that's the intuition here. Because of these deviations from being spherical, that black hole eventually is going to have a spin. Now, since I'm waiting for some time, you can think of some of them as being some of the angular momentum being there from before formation, some of them being accreted after formation. So it's not easy to very sharply separate these two regimes.
You also need gravitational waves when you have a
Yes. Yeah. And that would also be proportional to these deviations from being spherical, yeah. Okay, so we have this subtlety, and we want to be able to define angular momentum and mass properly. So what do we do? Let us think about this. In other words, we need a hierarchy of scales. And so let us remember how the various parameters scale with time. So we are in radiation termination. So A goes as a square root of t. Therefore, H goes as 1 over 2t. If I consider, now for instance here, what I have done is I have considered some range of scales that have enhanced power. So imagine those range of scales, when they enter the horizon, many black holes are being formed. But I also have large fluctuations at those scales which don't form black holes, but they lead to much stronger acoustic waves compared to the ones that we see at the CMB. So those are also important to take into account. So for instance, if I ask about the frequency or the physical wavelengths of those, those modes are also stretching. So I will have the following hierarchy of scales. At a time t, which is much larger than the size of the black hole. So the black hole forms when those scales enter the horizon. And the size of the black hole will be more or less of the size of the horizon at that time. Size of the horizon, remember, is of order of 1 over h, which is t. So this is the hierarchy of scales that I'm talking about, after I wait long enough. I have Rg, I have the wavelengths of the physical wavelengths of those perturbations. So it's A over k star. That is the square root of Rg times t. And then I have the horizon scale t. Rg is the gravitational radius, the size of the black hole. 2gm. So now, as you see, as I wait longer and longer, I get this separation of scales. The horizon size becomes larger, the wavelengths of perturbations stretches because of the redshift. Now I can find this nearly Minkowski frame at some distance r, which is between these two. And those Minkowski inertial observers on those in that region, they can ask unambiguously ask about the parameters of this black hole. And in GR we have expressions to determine those parameters. In particular, so for instance, ADM mass, ADM angular momentum. So in particular, I'm interested in J, the angular momentum, and that is given by the following expression. So there are various versions. If you look at GR textbooks, there are various objects that are ways to calculate this, I'm going to write the ones that is more convenient for my purposes. So this ji is going to be epsilon ijk integral d3r over this region up to this region r. And this r is, again, is some distance which is much, much larger than rg, but much less than rg, the square root of rgt, the wavelength of my perturbation. So I integrated over, maybe I write this here. I integrate the density of angular momentum that is defined in terms of this object, which is called the pseudo tensor of energy and momentum, tau 0k. So this is a pseudo tensor, which means that choosing a different hypersurface, because this is a calculation done on some hypersurface. This is a pseudo tensor because some perturbing that hypersurface changes this in a way that is not, the transformation of this under those changes of hypersurface is not like a tensor. So this is not a tensor. However, this integral is a tensor, gives us a vector. This expression does give us a vector. So the idea is that I'm integrating a pseudo tensor, but once it is integrated, it gives me a well-defined vector quantity. As long as I am asymptotically Minkowski. So as long as I keep this condition that I want to be asymptotically Minkowski, it doesn't matter how I choose my slicing for this final result. Okay, now now it's easy to see why J1 is 0. Let us first calculate J0. So there is this tau 0k, the density, the 0k component of this pseudo tensor of energy momentum. By the way, if we are in Newtonian limit, this pseudo tensor of energy and momentum is just the usual energy momentum tensor that we talk about, because the gravitational contribution is negligible. However, here it's not, that is not a good approximation because we are talking about a black hole. So this can have large deviations from the Newtonian answer. But one should keep in mind that this is the expression that if gravity was weak, we would have written to calculate the angular momentum. Where here we would just plug the T mu nu or T0k of matter. Now, what is this tau 0k? Let us calculate it. So we said that we want to use a perturbative scheme. So we can calculate this tau 0k perturbatively. So at 0th order, so what is the properties of this perturbation theory? We have a spherical symmetric peak that is collapsing. That's the 0th order solution. So the 0th order solution has the spherical symmetry. Therefore, at 0th order, this tau 0k, which is a vector, it can only have the following form. It can be just some function f0 of r times r hat k. And if I plug this in here, so this epsilon is a fully antisymmetric tensor. If I plug this expression in here, because of the antisymmetry of epsilon, I will get 0. That is, of course, what we expected. At 0th order, J has to be 0. So we move on to the first order. So this is first order imperturbations. Now, in first order imperturbations, of course, I can still have this vector r hat k available with a coefficient that can depend on my perturbations. So that I call f1 times r hat k. So f1 is the quantity which is linear in the perturbations on top of my spherical symmetric solution. But on top of that, I can have gradient, decay of some G1. Again, this G is a function that is linear in the perturbation. Okay, now if I plug this back in here, the first term, it gives me 0 for the same reason as this 0th order term vanished, because of the anti-symmetry. The second term also gives me 0 if I plug it. So let us see it explicitly. If I consider epsilon I j k integral d3r rj decay of G1. So how do we see that it is 0? We do a partial integration. So if I do a partial integration, I get 2 terms. So epsilon I j k, I get a boundary term at r equals big R. The integral is over the sphere at r equals big R. So let me just write dA as the area element of that sphere. And then, so I have G1, I have Rj, and then I have to put a normal to the surface, n hat k. But n hat k is just r hat k, because this is a sphere, so the normal to the surface is r hat. So I get r hat k here. Again, because of the anti-symmetry, it vanishes. And then the other term, and then there is another term. When I do partial integration, there will be another term, which is, let me write it up here, integral d 3r, r less than big R, G1, and then I act by the derivative on Rj, I get delta of jk. Again, because of the anti-symmetry, it vanishes. So what is the upshot? The upshot is that this whole thing is 0. This is equal to 0. So therefore, J1 is also equal to 0. So I proved the claim. Now, what about J2? J2, there is no reason for it to be 0. So I expect it to be as large as it can be, or a order of whatever we expected, which means that we expect J to be of order of mRg times zeta RMS squared, or in other words, J RMS to be of order mRg zeta RMS squared. Yes.
Why tau 0k for the first order has not terms with derivatives?
It has not what?
Derivative terms with derivatives somehow.
At first order? You mean this?
Why it has not derivative terms?
Oh, here because the only it's 0th order in fluctuations, right? So it's just a function of r. You can write the derivative of a function of r, but that would be proportional to r hat. Right here, this is the expression which is 0th order in your fluctuation. So you want to construct a vector in a spherically symmetric configuration. The only vector that you have in a spherically symmetric configuration is r hat. Mm-hmm. Other questions? Yes?
I think I don't understand your definition of JI, because you said that you are in a regime in which you expect to have asymptotically Minkowski, right?
Yes?
Also, it differs from what you would expect if you have weak gravitational field. So I don't understand why is this reasonable to define JI in this way. Maybe I don't understand your definition. If you can explain again.
I guess I don't understand the question. You are asking, you don't understand this expression?
Yes.
Oh, okay. So this expression is valid no matter what. It's not an approximation in the weak field. It's supposed to work even when you have black holes or everything. This expression is something that if you use Einstein equations on shell, this reduces to the boundary term that is called the ADM angular momentum. But it's, as you see, it is useful for me to work with its integral form, its volume form. Okay, so now you could be skeptical of this claim. For instance, you could ask, how do I know that there is not some mysterious symmetry reason for which J2 vanishes? I showed that J1 vanishes, but I didn't show that J2, I didn't show that there is no small parameter here suppressing this, or maybe even zero. So to give some, so I cannot rule out that possibility. Yes.
I'm more worried with other powers of RG coming in, because if you have things which are anisotropies inside your system, then why you only have one power of RG and not, say, something that depends on, I don't know, why can't I have other powers of RG showing up? Because we have derivatives there also, right? And
well, I'm just
this
constructing.
is the part of the argument that I don't quite understand.
Not that it's psi squared, that I get, but RG only one power, why?
Well, yeah, this is just dimensional analysis. You can think about the dimensionless quantity that I'm talking about, and I'm writing a perturbative expansion for that dimensionless quantity, and the parameter of perturbation is eta RMS. That's it. So now to give some a bit of more evidence for why I expect there is no big suppression here. Yes, so I cannot calculate the second order answer, and you can see why I cannot do it, because that would be doing a second order perturbation theory, relativistic perturbation theory on a background which is T and R dependent. So it's totally hopeless.
Sorry, why don't you have something like big R squared over RG? Because integrating all the way up to big R, anisotropy that you have in there. So why don't you have like big R squared over RG?
Well, that was the. The reason is that. The reason is that I expect that this region up to big R should be mostly empty. So so that was the reason why I wanted to consider late enough time so that the perturbation has been diluted enough.
So matter collapsed to the interior.
Yeah.
Voided everything out.
Yeah.
Integrated to this.
Right. So this R cannot be too large, because if it is too large, it's true I'm going to get extra contribution from whatever matter which exists. So that's the importance of the existence of this hierarchy of a scale. Yeah. For instance, it would be similar to asking about the spin of the black hole at the center of galaxy, if I stay too far away, the angular momentum of the whole galaxy would dominate it. So I have to be close enough to that black hole to measure. So one thing that I can do to give more evidence for this result is that, of course, I cannot do the full problem, but I can do the following calculation. Let's actually go to this regime. So what happens in this regime? Let's think about it. Where do I write? Here. So we have formed this black hole. There is a little black hole of size Rg. And then it sits on the background of some long wavelength acoustic waves. So one thing that one can ask is that what is the accretion rate of mass and angular momentum into this black hole? Now, why do I expect there should be accretion of angular momentum, or in other words, torque on the black hole? The reason is that so first of all, what is the situation that we are dealing with? We have some density, background density, rho bar of this fluid, but this fluid is also perturbed. There is some delta rho over rho, and there is some velocity field of the fluid. Now, so the very fact that I have a black hole sitting in some background fluid leads to some accretion rate for the mass of the black hole, because the fluid is going to flow inside the black hole. That's called Bondi accretion. And that rate of the accretion, or m dot, of mass is something of order of the area of the black hole, so 4 pi r g squared times c, the speed of light, times rho bar, with a coefficient that one can calculate given some particular equation of a state. Like, for instance, in radiation fluid, here there will be something like a square root of 3, or 3 times the square root of 3. Now, if there is a velocity of this background fluid, which would be there if I have these acoustic waves, that velocity would also lead to a force, which is P dot. And that force will be just m dot times v. And now if I have a velocity field and also a gradient, now you can imagine why there will be also a torque, because say there is a gradient in this direction. So this is grad rho, and there is a velocity in this direction. Then the amount of mass that I accrete from the top will be more than the amount of mass that I accrete from the bottom, and this gives a torque to the black. So that is also something calculable. These are calculable because I'm dealing with the long wavelengths acoustic wave. So I can use a gradient expansion to calculate this quantity. So to leading order, this J dot will be given by m dot times Rg squared times grad rho over rho cross V. So let's make sure it has the right units. I have rho over rho is dimensionless, V is dimensionless, grad is 1 over r, so mRg dot gives me J dot. And again, there is a coefficient here, which is something like 0.8 or so. So why is this expression useful? So first of all, you can already see from here that why I'm getting a second order answer. In reality, though, the reason is just the fact that the angular momentum is an axial vector. And if we have a scalar perturbations, we cannot construct an axial vector out of a scalar, a linear order. We need to go to second order to construct an axial vector out of a scalar. So that's why we need to go to second order. And one thing that we can see is that one thing that we can do with this formula is that we can, now that we have J dot, we can integrate it and talk about something called delta J of t, which is the integral of this J dot from t to infinity. So I calculate all of the angular momentum accretion over after some time t, and then I can ask, first of all, I can ask about the statistical property of this. So delta J squared of t, the expectation value, which I call delta J RMS squared of t. So what is this? It's the amount of angular, the RMS value of the angular momentum that is accreted because of these acoustic waves that I have in the fluid. And of course, this is something that if you plot it as a function of time, it goes down very rapidly because the density of the fluid is just diluting extremely fast. We are in radiation-dominated era. Rho goes as 1/8. So this is something that is dominated by earliest time. And of course, at earliest time means that it's dominated by the time that my perturbation, my approximations are breaking down. So what I can do is to do the calculation where it makes sense and do an interpolation, extrapolation to earlier times to get an estimate of what would be the full delta J. So that's something that I can here schematically plot for you. So this will be, want to plot this delta J RMS as a function of t. This is the important time, t equals RG. And then we can, this calculation is valid when t is much larger than RG, and we see that it's going down. So if we extrapolate it to early times, then here it gives us a number of order unit. So this gives a second order contribution to J2. Sorry, here I should divide also by zeta RMS squared. Now it's probably not legible. So we are plotting delta J RMS as a function of t divided by m RG zeta RMS squared. So remember, this delta rho over rho and v are linear perturbations that are related to our original zeta perturbations. And I'm using that fact here. So this extrapolation gives me an order 1, puts an order 1 coefficient in this expression for J2. Or J. And this argument says that it shows that even if there is some cancellation between the initial contributions and the late time accretion, one does not expect 100% cancellation because we are talking about these waves, acoustic waves that we are talking about, they are propagating. So at later times, they are coming from different regions compared to the early time. So 100% cancellation seems very unlikely just because of causality. Well, one cannot rule out 100% cancellation. So anyway, what does this predict? This predicts that the spin parameter of the primordial black hole, which is this J divided by mRG, it has to be something of order of 1%. Because zeta RMS that we have to get any reasonable number, density of this black holes is of order of 10%. So we should expect a percent level spin parameter for the spin parameter. And yeah, this is not within the within our precision today to measure this, but it's not totally unimaginable that we get to that level of accuracy in the future. So I think I'll stop here.
So if we think about these primordial black holes as seeds for later black holes also, I mean, if you're thinking just about dark matter, then sure, this is, you would have huge numbers of small mass black holes with a small angular momentum, but then you think of seeds for larger scale black holes, but then that you can regard as an initial spin, right? Mm-hmm. That is going to then be erased by the contribution of all the accretion of material later. So in that case, you can also not measure that, right?
Right. Yeah, this is essentially the initial spin. So if there is some future environment, then it can build up.
Erase that.
Yeah.
More questions for Mehrdad?
When you were discussing the peak in the distribution, you said that during the formation there's the possibility of emission of gravitational waves. So, does this emission affect another quantity, another observables? It's possible to use that for something?
Yeah, in principle, yes. It's so it would depend on the scale or the mass at which this process is happening, right? The mass of the black hole determines the scale, and that scale will determine the frequency of the gravitational waves that are emitted. I haven't done this calculation to see like what would be, how significant they would be, and yeah, what would be, for instance, the mass range for which they are observable in the near future experiments. Yeah, I don't know the numbers, but in principle, yeah, this is a possibility.
Because if you have a measurement, then you'll be able to. There's a real correlation between the gravitational waves and the distribution of the primordial black holes, right?
Yeah. If we. Of course, to correlate them, you need to measure both. At the moment, we have measured neither.
Questions? So I have a favorite joke. My favorite joke about primordial black holes is dark matter. So if 30 solar mass black holes are dark matter, I hope there's no direct detection. A few people got this. Okay. So I just want to remind you that on Sunday there will be a round table. So you're all invited to come. As Rose said, there will be good food. So it's a good motivation to come. Mm-hmm. So let's thank Mehrdad again for this very nice seminar.
Yes.